Okay, so the first thing I want to deal with is the question of this. Remember, when we define Harishchandra pair, there was a semi-simple Lie algebra G, and there was an algebraic group with a morphism in into G with differential which is injected. So this is just G. So we can basically K can be a cover of its image into G. And one of the statements I made is that if G naught is connected with real semi-simple Lie group with finite center, and K naught maximal compact subgroup. And I mean, there is a classical theorem of Dragan that all such maximal compact subgroups in a real Lie groups are conjugate, then I can consider the complexification of K naught and it maps into G, therefore K acts on the flag variety X. And the theorem I want to prove that K has finitely many orbits. So this means that GK is the Harishchandra pair in terminology of last lecture. Therefore, I mean, we can apply the theorem we proved last time on the category of Harishchandra modules to this, say, classical situation. Okay. I don't know the history of this result. I mean, there are several people who claim that they proved this, but Laurel claimed, I knew this in the early 50s. So this is something classical, but I don't know the proof. I will explain this classical, and you will see it's very simple because it basically follows from Rupas. So what do we do? First of all, the critical observation is that the Lie algebra say K, yeah.
The two things. So firstly, so last week, the first thing I plus thought is the definition of everything. And then you're saying this will be example.
Yeah.
And can we just, because there's too many members, could we just have one example given them of G? I mean, I know it's
you know, I mean, say SL2R and maximal compact is say SO2. And if you look at complexification of SO2 is C star, and the flag variety of SO2R is one dimension, is Riemann sphere. And if you calculate the orbits, I mean, basically, if you look at projective coordinates here, then this C star acts by multiplication by the square. So if you do the calculation, you see that there are 2 points, for example, 0 and infinity, depending how you parameterize this, and they are closed orbits, and C star is the ultimate and the finite event. So we want to generalize this fact. And the main observation is that this will make the proof work, that if I look at K naught, then K naught is, there is so-called Cartan involution. So sigma squared equal to 1. So its eigenvalues are plus and minus 1. And K naught is just the eigenspace for eigenvalue 1. So this follows from structure theory for real semi-simple E groups. So we can extend the sigma by linearity, and we get an involutive automorphism. Yeah, I mean, I should say this is an automorphism of the complex Lie algebra G, and then the Lie algebra of K is fixed points of this Cartan involution. And this will make our proof work. Basically, we can think of K as fixed points of the lift of the Cartan involution, say, to into G. Since, I mean, central subgroups are irrelevant when we look at the action on the flag variety. So, yeah.
So my story for this is that if you try to find the real form will be some n holomorphic, but then you have this canonical n holomorphic thing, and then you can find it.
You have compact conjugation. Compact conjugation defines compact form, and then you multiply by this, and then complete that. Yeah. So this is behind all of this, but basically the only thing we need, and so this is kind of motivation, is that Lie algebra of K is a fixed point of an involution of G. We even don't care. Yeah. So everything follows from that. And now let's prove this. I have to set up something. You will see the proof is more than simple. So we look at 2 copies of X, of the flag variety of X, and we define the action of the group G. So I'm just calling this G for simplicity. So I define that G, say XY is, I apply the action to the first coordinate, just the standard action, and then I twist the action by sigma to the second variable. So this is this twisted action on x cross x. And let me count the orbits of G under this action. So if I fix a point, say U, then of course I can move by the G action second coordinate wherever I want. But to check the orbits, I consider E to be the sigma applied to B of U. B of U is Borel subgroup in G corresponding to the point U in the second copy, and I twist it by sigma. So then if I look at xy, xy to be conjugate to this VU, I have to x is GV and y is sigma G of U. So if I want to count in Gx transitively on the second coordinate, I can move it everywhere. So any G orbit, it intersects this slice where U is fixed and V is variable. And if I look at the map, which attaches to a G orbit O, the set, which consists of, say, V U, V in O in the let's see. Look at my notes. V in X, such that V U is an element of this order. Then this means that okay, and W, as I already used. So since the stabilizer of U is this P, then we see that these W's are in a B orbit in X. So we see that, so this is a B orbit in X. Therefore, this map is a bijection between G orbits and B orbits, G orbits in X cross X and this action, and B orbits in X. So by Bruja's lemma, this is finite, so the number of G orbits is finite. So this is the first step, which is just Bruja's lemma. And now we are going to do something more interesting. So we consider delta is diagonal in X cross X. Then, first of all, by the definition, the diagonal is K invariant. Moreover, I can the orbits O also K invariant. So I mean to point out that K on an element of diagonal acts just kx, so delta. And we see also what will be important a little bit later, that the map, say sending x in x cross x, it establishes bijection between k orbits in x and k orbits in the other. So if I look at delta intersected with O, then this is a in red. So now let's see what we can do. And of course, the k orbit that k is connected are connected. So I mean, if I look at these intersections, there are k-invariant subsets. They can have a bunch of components in general, but k orbits will correspond be contained inside one component. So I want to see what is the difference. So let's take a point xx in delta intersecting O. Then I can look at the tangent space at this intersection. So first of all, let me, the tangent space at the flag variety at the point x, I can identify, I mean, if I look at orbit map, which I denoted by, say, omega g is g applied to x. Then, first of all, and let me denote by p of x the projection of g into g mod bx. Since bx is the Borel subgroup corresponding to x, so there is p of x is natural projection here of g into tangent space, which is a differential of, I think we call this tau. I don't know. Tau x is the orbit map from g into x, which is tau x, like g is g applied. So if I look at my orbit map here, so this is g x sigma g x, then I see that the tangent space O is the set of is p of x c p of x sigma p for c in g, and to be inside the time, I mean, in the intersection of the tangent space of the orbit with the tangent space with diagonal, I mean, those coordinates have to be the same. So if I look at p of x, it all intersected p x x of the diagonal. This is a set of these p x sigma c for c in g, but also such that p x c is equal to px sigma c. And then if this holds, this is also equal to Px of 1/2 P plus sigma C. So if we look at this, we see that this intersection is nothing else than, so this intersection of these two tangent spaces is Px P, Px P, or C in K. And on the other hand, this is clearly the tangent space at the point xs of Q, where Q is K orbit through the point xs. So the conclusion is that the tangent space of the K orbit is in the intersection of these two tangent spaces. So basically, this orbit is open in this, and we see that it is a component. I mean, just by varying axis, it's component of the intersection of the orbit with delta. So, and since there are finitely many of orbits O, and the intersection has finitely many components, this implies the finiteness of K orbits. So we are going to see, probably next time when we actually start discussing the structure of this set of orbits in this case, another way to see finiteness, but it's based on another result about Cartan subgroups in semi-simple groups, which is probably equally technically complicated to prove as this one. But so this is the first thing I wanted to prove today.
So this also gives us the labeling of tails by elements above.
Yes, I mean, one could use this to get the set. But we are also going to have when we discuss the other one to label them in a slightly different way is related to this, but this way will be closer to the point of your people representation. They will be attached, or it will be attached to function of the classes for Cartans, which is stable in the Cartan. So, for example, in the case of SO2, we have two conjugacy classes of Cartan: compact Cartan and split Cartan. And 2 points attached to compact Cartan, and open orbit is attached to split Cartan. In this picture, general. And I mean, in a way, this is something which, at least for people in the field, seems more natural because parameterization, because I think a long time ago, probably even in the 50s, Sujura classified all these conjugacy classes. Costa and Burrell proved they're finding many conjugacy classes and how you can parameterize, and Sujura has a paper in that page for any real pool so people know how this is.
Do you want to write it down in concentration?
Cardano evolution in the case of SL2R, I think is just transposing and inverting. Yes, the group. I mean, you want to get a definition of orthogonal matrix, and of course this works for SLNR. I mean, I just put out SL2 because I could describe the orbit. Okay, any other questions? I just want to raise this and start and talk about it.
Somehow all of the so cable from GMOD just more complicated than this. But somehow all the complexity arises when it's innocent intersection of numbers.
Yeah.
They kind of really focusing up on never control.
Yeah. The only, I mean, nuisance is, if you compare it highest weight, is that orbits are not topologically trivial. See, so you get, I mean, I'm now jumping ahead, but you get a non-trivial fundamental group for the orbits, so the D modules attached to orbits won't be as simple as in the case of highest weight category, where the D modules on the orbits are just structure sheaves, and so basically, say irreducible is high weight category of parameterized by orbit. Here you will have orbits plus some additional information which depends on the topological complexity. Okay, so the next topic is discussion of irreducible holonomic modules, because last time we proved that, say, localizing Harishchandra modules, we get Harishchandra sheaves, but Harishchandra sheaves are lengths are holonomic, so they are of finite length, so therefore they are built out of irreducibles, and we have to describe these irreducibles. And I want to explain to you why, why the parameterization of irreducibles is almost trivial. Of course, unfortunately, then you get what you pay for. I mean, irreducible Harishchandra modules are global sections of these irreducible Harishchandra sheaves, and we don't know at first glance anything about those. Okay, so this is what I want to discuss, that irreducible. I mean, at the beginning, I will discuss irreducible D modules, and you will see that all the proofs are completely, I mean, the twisting is completely irrelevant. So to make the discussion applicable to more general situation, and also to show that this is really technically very simple, I will just assume that they have a smooth algebraic variety and D modules somewhere. And first we need something called extension lemma, which is usually attributed to Grothendieck. So let B be quasi-coherent or X module. I'm sure that Grothendieck's definition was much more general. Some scheme with some technical assumption possibly on X. So if U is an open set in X and U submodule of, is it better? Okay. And let me assume, I mean, don't be mad at me that I'm pointing out trivialities, but this is a submodule in category of quasi-coherent homodules. We can define Q bar, which is the U bar on an open set V is the set of all sections S in V on V such that the section restricted to be intersected with U is U of V intersected with U. So basically what we do, we create a sheet on X such that for any open set, I mean, we take all the sections which restrict to U in that section of this section. And the statement is that this is OX, is quasi-coherent. First of all, if you look at U bar and restrict it to open set U, then you get U. So U bar is in some sense extension of U, and it's called canonical extension. Okay, I mean, I'll prove it in a moment, and the proof is very simple. But the why this is important, because it has the following corollary. So let V be an irreducible OX module. Oh, okay, let me see. I don't care about OX modules. Then, so U in X open set. Then V restricted to U is either 0 or irreducible. So this is, in some sense, in the first glance, crazy, but this makes everything work. Of course, the corollary, if you think about this, I mean, by irreducible, I mean irreducible in a category of quasi-coherent DX modules. So I take an open set U, I restrict it, and let's assume that V restricted U is not irreducible. then it would have a sub dx module, the u module, say u, and we would be able to take canonical extension, and of course, canonical extension of D module is a D module for obvious reasons. So this canonical extension should be V, but then this U has to be equal to V of U, or the other possibility is that it's 0, and then V restricted to U is 0. So we see that this is either 0 or irreducible. Okay, so let me prove this lemma. So let's denote by I the inclusion to X, and let's denote by W the quotient of V restricted to U by, how did it call this, by U. Now I can, so this W is quasi-coherent, so I can look at I star W, and I mean, this is the critical point, that this is quasi-coherent of X module. If what we know that this is actually, this is what we use, this is sheet theoretic. Directly. This is the adjoint functor of the restriction. So we have form of the restricted to U, W is on B W. So if I look at this canonical morphism here, it gives me a map of V, say P, from V into I star of W. And now the point is that if you look at the kernel of P, and then this is just U bar. So since quasi-coherent OX modules form an abelian category, we know that U bar is quasi-coherent. Another, let's see, before we, yeah, so before the break, I just want to observe one fact, which is also trivial. So we have a corollary also that let B be irreducible so I mean the proof is straightforward following say this discussion here, because if I take a point X in X and I take U to be open up by neighborhood, then either V restricted to U is 0, or the add on be restricted to U is irreducible. Then essentially by the same argument as Sayre's theorem about O modules on affine variety, one can prove that in this case, the global sections of V restricted to U are irreducible module over differential operators in U. So it's generated by any non-zero section. So we can write resolution. I mean, we can write it as the U into global sections of X. And if you localize this, we get the same statement. And this tells us that V is coherent. And this, so in a way, you see now that what we were discussing last time, that if you take a reducible D module, then it's coherent. So we can talk about its characteristic variety, but the characteristic variety can be big, as we discussed last time. If it's holonomic, then of course this is not the case, and we know that Harishchandra is a holonomic. But up to this moment, we didn't use Milicic at all, so this will be used later in the argument. Okay, so this is probably the place to start. Any questions?
Maybe just to comment on that, Robert, because I think it's like remarkable. And if you think about like the thing on the cross, like the support on the cross, then as if you take the structure sheet of the two axes, then as a coherent sheet, you can have an extension which glues the two together. But as a D module, the IP extension does not mix the two axes anymore, which is a quite remarkable to see. If you consider a cross, so this would be a coherent sheet, like very vaguely, a coherent sheet counterexample to this state. Because we have something, I mean, very vaguely. Okay? Because we have something that's stuck together and we remove this point and it breaks into two pieces. Very, very vaguely, yeah. But what is not vague is if you think about, like, imagine that we remove this point, and then I take an IC, I take an IC sheet supporting on this, so it's supported on this. So this is like, you can think about this as being its functions along here plus this kind of funny direction that comes from D module. And then you have the corresponding D module on this axis. And when you do the intermediate extension, they do not mix at the origin, which is kind of surprising if your intuition comes from coherent. I feel like we're doing that. We should do
Yeah. Yeah, and of course, I mean, people who play with sheets without quadratic coherence think immediately the irreducibility doesn't make any sense. Because you take just stalks in some arbitrary ways, put them in two families, and the thing produces.
Well, like if you take intractable shape on C, then constant shape is an infinite has a submodule corresponding to a street extension.
Yeah.
Let's say you remove any number of points. Infinitely. So imagine that I have C without Z1. And I include it inside C. Oh, sorry. I didn't like that, but anyway. No, I do actually like it. So you can take the extension by 0 of the constant sheet on, let's call this UN. And this is injected in good old construction machines into the constant sheet on C. And now I can take more and more points. And so this is an infinite length in construction machines. Or another way of saying it, this surjects onto any number of state vectors. And so these are things like the finite length property of D modules in diversity is very surprising. But yeah. And so when we dig into the characteristic Dragan, it's very clear. And in fact, yeah. I mean, this example from the point of view of characteristic cycles is fantastic.
I mean, this is actually what we are just proved, because we are going to classify all irreducible polynomial functions. And basically the answer is the support is irreducible. This is the moment. And then you take a smooth, open, dense subset in the support. And there is a connector. And when you take direct image in category B modules, this direct image has a unique reducible stuff. And this is your irreducible. You think, no, I mean, why? I mean, we are now discussing without any rule search. Oh, you were thinking. I mean, at the moment, this is just, I didn't say it very clearly. I just wanted to de-emphasize the group for the moment. This has nothing to do with flag variety, the group. It's just good old modules on a smooth variety. So if I ran out of time, this could be an exercise. So let me an irreducible module. Then is irreducible. Yeah, I had to remind you that we had this discussion couple of classes ago about the definition of support. So the definition I'm using is that support is always closed. So I can look at collection, say F, all U in X, U is open, and V restricted to U is 0. And this collection has a maximal element and its complement is the support. So this is the largest, I look at the largest open set, the restriction is 0. Complement. So this guy is by definition closed, and the statement is that this is reducible. But because of this discussion we had, I mean, this follows easily by applying the extension lemma, but I think I will postpone this for a moment and discuss this other part, which is I was tempted with our discussion to explain this as fast as possible. So let's assume that we have our smooth variety X, and we have U, which is open X, and then we have say if V is irreducible on X, irreducible V marginal on X, that V restricted to U is either 0 or irreducible. This is what we just proved. But let's look at the opposite construction. So let's consider, say, U irreducible on U, and then we can form I lower star of U, where I is, as before, the inclusion of U into X. This is clearly quasi-coherent D of X module. I mean, that it's D of X module is obvious by the definition of theoretic direct image. Quasi-coherent is this, the result we already used. So it is also the right adjoint of the restriction. So if I look at home, the D of U, and say W restricted U into U. This is the same as on D of X W I dot direct image. So first observation is that there are no, so if support of W is in the complement of U. So I have some, this is my X, and I have U here. And I have something supported if the outside of U, then I mean this is 0, so this W cannot be a submodule. I mean, it cannot have mapping into I lower star of U is non-zero. So the first observation is that I lower star of U has no submodules. Supported outside of set U. So in particular, if V is a submodule of this direct image, then V restricted to U has to be non-empty. non-zero. Now, if by our assumption, so this V restricted to U is a submodule of U, but U is non-zero, but U is irreducible. So V restricted to U is equal to script U. So now we cannot do much more. And this is what I wanted to point out because it's kind of, I think, helps to understand the discussion we had. In general, we cannot do much after this, but let's assume that U is also polynomial. Then the direct image functor for D modules preserves polynomicity for open embeddings. So this is I star. So there is a fact we should discuss at some point that the lower dot of U is also polynomial. Therefore, it has finite length and it has an irreducible submodule. So if I apply this argument that if V is an irreducible submodule of I dot with U, then V restricted to U is U. So we see that there exists an irreducible extension of U to X. And now, if I have another submodule of I lower star U, this submodule has to have this property. So its restriction to U is the same as the restriction of the first one, but this implies that they're both these are the same submodules. So let me just so how we conclude this? So let me actually write this down. So let W be another E of X submodule of I. Then by what we observe, W intersect the restrict to U is also equal to U. therefore, W was intersected with V is different than 0. But since V is irreducible, this tells us that W contains. So this implies that V is the unique irreducible sum of I dot. So, see, we started with being reducible, very restricted to an open set, and we get an irreducible module. On the other hand, if we take in a holonomic situation, if we take the direct image of an irreducible module on U, then this direct image contains a unique submodule which restricts to U. So we have a bijection between irreducible modules on U and irreducible modules on X. So with support and yeah. So yes, gotcha. So now, assuming this lemma, we can push this a bit further, because let's assume that we have V, which is an irreducible dx module. And so V is closed and irreducible. So I can take, say, singular part of the support. So there, so let V in support be smooth. And then so say a whole smooth part. Then is smooth. That's the Then I can take the complement, say Z is support. This set B, and consider U to be X minus B. So I throw away a singular part of support, and then by V restricted to U becomes irreducible D of U large. And it supports and inside U is smooth and closed. So we have this X and this U, and here is my support. Okay. So now, what do I know? I know that my B module here is irreducible. But if I look at this picture, that I see that in the following situation that we have a smooth variety and irreducible B module, which is supported on the C, which is closed, smooth double. I mean, I can actually make this V smaller if I want and assume that it's up, but it doesn't make too much difference. So this is all general nonsense. Now we get to something interesting. So we want to describe this irreducible module. And the way we are going to do this is that there is something called capillars equivalence to categories. Which says that, first of all, we can define direct image from B modules. So let me denote by J the length of B into U. So we can define direct image of J, say J plus from B modules from B into B modules on U. I mean, I will discuss this construction. Let me just, at the moment, give you the idea how it's if you locally, roughly speaking, you can think that you have a D module, you know how to differentiate along V, but you don't know how to differentiate in normal directions. So you just formally add. So for example, if your subvariety is defined by a function, we will take a vector field which is say non-trivial, and this function and apply its powers and take a direct sub. So this is almost like a construction of normal in general. And this is how you define direct image of B modules in this situation. And this functor is exact, and it's an equivalence of categories. since you can describe it locally, they just said you can calculate its characteristic variety. And from this calculation, you conclude that if the D modulo on E is holonomic, its direct image is holonomic. So basically, you get that the D modules on E are equivalent. The category is equivalent to the category of D modules on U supported in V. And this equivalence reserves coherence, holonomicity, and of course, for obvious reasons, irreducibility. So, this tells us that this irreducible modulo U, which is supported on this smooth subvariety, is actually a direct image of some D modulo on V, which is irreducible and holonomic. And of course, its support is V, because this is how we constructed this. So then from Jordan's discussion, we know that its characteristic variety is, except on the set of lower dimension, is just the zeros. Because, I mean, holonomic module, the characteristic variety has dimension equal dimension base. Its support is everything. The zero section has to be in characteristic variety. But it will be only zero section generically, otherwise characteristic variety. Yes, generic. So this means that if I shrink my V, so here, if I take a slightly bigger part of the support, then actually I can assume that our D module on V is a holonomic module with zero section equal to its characteristic variety, and then such module is a connection, so it is locally free OX module of finite rank, and this gives us the answer that there is, if D is sufficiently small, there is an irreducible action on D, which if it's pushed forward by the inclusion of V into U, and then U into X, gives us a holonomic module, which is actually the direct image of the composition. It's a composition of direct images. So you get the map from V into X, and the direct image from our connection gives us the holonomic V module X, which has the unique irreducible sum, which is our image. So this gives us that the parameterization of all irreducible holonomic modules. Does this make sense? So,
I just have to part of the dilemma. The irreducible D module. So there's no homogeneity continuum.
No. And this just follows from the saying that we know this for even. And this is enough to show that support is changed.
I misunderstood, so that was kind of obvious what was there before, and now you're going over the final.
Yeah, I mean, I just, because we have this discussion about IC keys, I want to see how the structure of the argument works in the D model. Okay, so let's see what they have. Okay, so let me just wrap out this big picture, and next time you're going to fill in details. So related to Jordan's question, let's see how this works in the situation of our Chandra sheets, where we can be more precise because our supports kind of vary. So I mean, polynomicity is critical at this point that I lower star U has an irreducible sum. Everything else is kind of, except of course the fact that this is a connection at the end. So let's discuss our irreducible now something didn't color. So let me change the color. So let V be an irreducible Harishchandra. Then it's irreducible as a D module. So this requires a little bit of proof, but it follows from the fact that K is connected. If you, the twisting with the line bundle clearly preserves irreducibility because I'm twisting by negative of this, sends it back. So we can always assume that we are inside the chamber where we have equivalence of categories. So James and Bernstein chamber. And there, if I have an irreducible Harishchandra sheet, the global sections are irreducible Harishchandra module, but since K is connected, then being irreducible means being irreducible as a module n over n over algebra. And then this tells us by localizing, this means irreducible as a D module, and then you twist back and you say that this is an irreducible D module. So then the lemma tells us that support of V is closed and irreducible, but it's also K invariant. Since the group acts on our Harishchandra. So therefore, support of V is union of finitely many k orbits. But then there must be a k orbit which has the same dimension of support of P. So let's denote it by Q. And Q is dense in support of P, and since support of V is irreducible, Q bar is support. So we attach to V the orbit Q, and now our discussion here tells us that if we have this orbit Q and our irreducible D module is supported on the closure of the orbit Q, so we throw away, we consider the X prime is X minus the boundary of Q, and then our D module restricted to X prime, it stays irreducible, and its support is Q, and Q is smooth and closed subvariety of X prime. So by previous discussion, it's a direct image of a D module on Q, which is K equivariant. So the characteristic variety, since Q is in orbit, must be everywhere the same, so it must be zero. So what do we get? We get on Q, we get the connection tau. So this is a K equivariant connection on Q. This is the second piece of information. And if we have this, then we take tau and we take a direct image. The J is Q into X, and then we take J direct image of tau is equal to something I will call I Q tau. So this is standard Harishchandra sheet. Then the standard Harishchandra sheet has a unique, irreducible sub. Say, let's call it LQ tau. And V is isomorphic to LQ tau. So if you look at this more carefully, you see that this gives you a description of all irreducible D modules, Harishchandra sheaves. So they are parameterized by K orbits, and to each K orbit, you can attach finitely many, I mean, we have to discuss this more carefully, connections on Q, because these connections have to be compatible with the twist of D lambda, and this implies finiteness, so there are finitely many connections. And so these parameters are called geometric data. And if I have this geometric data, then the corresponding irreducible Harishchandra sheet is a unique sum of this standard Harishchandra sheet. And this gives us a classification of all irreducibles. And we see that there are finitely many of them for any lambda. So this tells us that for a given infinitesimal character, there are, by equivalence of characters, there are finitely many irreducible hypotheticals. And this is, say, again, for highest weight modules, this is easy to prove without any sophisticated tools, but Arishchandра's proof of this finite is extremely complicated. Use regularity characters. So this is much cheaper and simpler explanation of that fact. The point is that to classify irreducible Arishchandra modules, you have to calculate cohomologies of these LQ cows, which seems impossible. But cohomologies of standard IQ taus, this can be done. So this was done by Hecht, with Wolf, and myself. And basically they are given by cohomology connection. So there's a completely algebraic way to describe the cohomology. And I think it's right time to stop.